All right, so I am Mary Thomas. I'm a computational data scientist, and I am also part of the Data Enabled Scientific Computing Group, and I'll talk about interactive computing. Well, interactive high performance computing. There's a lot of different kinds of interactive computing, and I'll talk about that today. So let me get in here. So the complex program, this talk today is part of a series of webinars covering topics for people that we view as being part of the non-programming computing. That means you're not doing coding for your application or your scientific domain, but you're not writing parallel code. That's a whole different series of topics, and it's for helping you onboard, get onto a system like Expanse or other systems like that, understand how supercomputers work, get a feel for using Linux, and we have several tutorials on the different topics that we think are essential for being able to work in an HPC environment. Complex stands for comprehensive learning for end users to effectively utilize cyber infrastructure. And again, we have a whole series, and I have links to it in my talk. And you're here because you found our talks. And in case you just don't know, there are many, many other topics that we cover. So in this talk, I'll talk about defining interactive high-performance computing. I'll talk about how to access and do high-performance computing on an interactive node. And I'll give you some examples of interactive computing, all with a focus on parallel computing. So parallel computing, HPC systems, you're here because you're entering a whole new world, or maybe you also facilitate people trying to run their work on these high performance computing, but you're here because you're entering this world of immensely amazing supercomputers that can do amazing computations. This shows fish monitoring and following fish, COVID calculations, astrophysics and black holes, muon tracking, planetary movement, and everything that takes so much amazing computational power to get some of the computational work done can be done on these supercomputers. And without supercomputers, the COVID models, for example, could not have been done during that first summer. It was able to, reduce the computational time down significantly. And that's your motivation for being here. But that's the good news. There are computers that can run your code at a much larger scale than you have been able to, especially like in the AI machine learning workspace. But the challenge is that you're going to have to run these on these HPC clusters. They're powerful, but they are complicated, and we know that, which is why we have the complex training series. Jobs can be run in different ways from the command line, what we call the batch queue system, or application clients, and I'll talk about batch queuing and some applications. And the jobs can scale from one core to thousands of nodes and thousands of cores on those nodes. It just depends on your job and the system you're running on. And for large jobs, we need to schedule those. It's kind of like if you go into the grocery store, there's registers, and if you can queue up intelligently to the registers, everybody gets their purchases made. But if you have one register with one big circly line, it might take you forever to get one item purchased. So that's why grocery stores, they model queuing systems pretty well. This is just a simple diagram showing a user on your laptop logging into what we call the login or the head node. And that's where system software and applications run that help you schedule your job. And then this interconnection network that connects these nodes. There's a lot of them, and I'll talk about Expanse. And you're very smart, but you're not going to be able to schedule thousands of job requests on a queuing system. So they have real advanced software, and we'll talk a little bit about that today. But we have a whole complex webinar on schedulers. So here's Expanse. If you've been to any of our talks, you see this. It's just not there to scare you, but to show you how complex it is. So when you're working and things go wrong, you can understand that it might be challenging for you. So we have a wonderful support team, consult at stsc.edu. They are there to help. Several of my team members are here and they're part of that consulting group. They'll help answer any questions you might have. So feel free to put those in the chat. I won't need to stop because I know that Nicole and Marty and Bob are here and they can address any questions you've got. But this is the complexity is that maybe you've never seen a computer rack. These are very tall. They're like 8 feet tall. And the lights are in there to show the wiring, and this is a cool liquid cooling system. But these are some of the racks that are in Expanse. And there's 14 in this diagram. We have a few more now that the system is built to grow over time. We have very large petascale storage, regular and object-oriented storage, and everything is interconnected with a very advanced network. To give you an idea of this scale, being one system located in our building on campus, if you look at communication across the internet by people with their iPhones, it's petabytes of data a day being exchanged all over the world using all kinds of networks. So you're actually, every time you pick up your phone, working on a supercomputer. Okay, so these jobs that we run, though, they're very special. They're high performance computing jobs. They typically involve the need to have a lot of nodes computing or a lot of data. And so HPC is the term that refers to what we'll be working with today. So jobs can be run as batch jobs, which run in the background. I give the job to a handler, the handler takes that job and runs it in the background. Or interactively, there are things that you need to do real time, like running a Jupyter notebook. Or working on the portal, and it gives you access to tools like MATLAB and R and other tools like that. But to get your work done, it has to get onto this big machine where there are hundreds of nodes and thousands of cores on just Expanse. There's some kind of resource manager, and the jobs get queued up into, remember those grocery store lines? Some of them are regular terminals and some are the, go through and do it yourself. And different jobs line up differently. And I'll talk a little bit more about that later. And when the job is submitted and running, it goes onto a compute node. And where possible on my slides, I do try to include a link to further data, like where the image came from. So that's background computing, batch computing. And in the batch computing, how do they work? So we use something called the batch job scheduler. The batch job scheduler helps figure out what goes in that queuing system. Any HPC or high throughput computing HTC system will usually have this cluster of machines, which means they need a means of sharing these resources fairly between users and intelligently. Without this, there would be some kind of machine anarchy. They'd want to, well, anyway, we have these batch queuing systems then that are called batch systems or the batch scheduler. They're intended to do this. They all have, every system may have its own batch scheduler, but you have a scheduler that you submit your information to, and it's responsible for allocating what CPUs are needed to do the job, CPUs, GPUs, and it manages one or more queues. We have different logical queues that we set up for our systems, and then these job partitions or job queues, you can configure these to be configured for a particular type of job. Serial parallels, CPU, GPU, long or short, large memory, not so large memory. And that's a way of facilitating the different kinds of job types that we can support. And so you kind of need to understand how the batch jobs work in order for you to run HPC jobs and interactive jobs on these clusters. So the batch scheduler main goals: minimize time between when you submit your job and it gets completed. No job should stay in the queue for long periods of time. Optimize CPU utilization so that the algorithms can maximize runtime and minimize idle time. Idle time for us is wasted time, energy, and valuable resources. Excuse me. Maximize job throughput. Get as many jobs running through and on the machine and through the system per time unit as possible. And support the running jobs automatically in the background so that you don't have to worry about it. You literally can fill out your batch queue request, go get your coffee, and come back and find out it's running, and then come back and find out it's done, which is kind of nice. unless you're not tracking it to see if something goes wrong. Then you might want to be checking it. And then finalizing your jobs. Ensure that the job data and all the results are recorded and stored where you want them. You tell the batch system where you want the data to come from, where you want it to go, and then other things like the environment and things that happen during what we call runtime all get stored for you by the batch scheduler, so you don't have to worry about it. And you can tell it the name of the output file that you want. So this is a simple batch scheduler. You're the happy user. You're logged into Expanse. By this point, I hope you've all logged in and you've seen some of our basic complex materials to help you with that. If not, every term you see in here, there's going to be some, most likely a complex topic to help introduce you. And we have webinars we've recorded, all of our talks. You can get the PDFs, all that, and Cindy's going to be posting that information. So you can go back and find those webinars and learn from them. Anyway, you log in, you build a job script, which looks just like a C shell, bash shell, some kind of shell, Linux, Unix environment. So you'll have a shell script with commands in it, special commands for the Slurm scheduler. And then you submit it to the job queue, and the scheduler then does a whole lot of work and orders up the jobs and launches them on the batch system, launches them onto the nodes when it's time. So you don't have to do that. It's not interactive though. These are all done in the background as batch jobs. And they're very convenient for a particular working environment and workflow that you've got. But sometimes you want to be interactive, and that's the point of today. So we have the Slurm Resource Manager is the simple Linux utility for resource management. And yes, if you know Futurama, it is named after the Slurm drink. And it's a big joke among the community. It's open source and runs on a lot of systems. And we think of it as a glue for the computer to schedule and run jobs. And its role is to allocate those resources within the cluster. And again, like I said, make sure everything is connected properly. There's data tracking, the information's getting recorded. It does a whole lot of work. It has a controller daemon. It has the batch daemon and a Slurm control, several control daemons. This is a list of a few of the commands that you might run for Slurm to find out what's running on the queue, to submit your job. srun is a command we'll work with today for interactive computing. And there's a whole lot of Slurm commands. And if you want to know what they are, go to this link on the page. So its function, again, the Slurm Job Manager prioritizes jobs, figures out where jobs should run and when they should start, terminate the job when it's done, get appropriate resources, and manage your account. So how scheduler schedules jobs. The simple example is here I've got 6 nodes 1 through 6. The users are going to submit 9 jobs all at once. They all get submitted. Some get started. Some might have already been running. And jobs 2 and 9 are what we call multi-node. And so job 9 is running, and this is time going by. And job 3 is running in parallel with job 9. Job 8 runs, it ends. Job 7 gets launched, it ends, and they're all on node 6. So you can see node 6 is being used for lots of small jobs compared to job 9 and job 2. So that's queuing jobs up, figuring out when they should run, and then when one job is done, backfilling and getting everything ready for the next job to come along. And that's, just in a nutshell how the scheduler works. So when you submit a request to the Slurm, you're waiting for your job to get sorted out among all the others. If you log on to Expanse and you write the SQ command, you'll see there can be hundreds and hundreds of jobs running and hundreds and hundreds, if not thousands more waiting. And you're just going to have to get right into that group to run your jobs. But it's fair. It's managed and developed to be fair so that if you have a tiny job that can be backfilled real quick, it'll run. If you have a really big job, then you might have to wait, but you will get your job to run. So what's interactive computing in the context of this? Right now, I like to tell people you're doing interactive computing right now from a computer science perspective. You have a laptop or a desktop, you have a web browser running, and you also have a lot of other applications running, maybe Microsoft Word or spreadsheet, you have your email client, and who knows what else you've got running. and multiple browsers, say inside of your Chrome browser. So you're interacting with all that software, and every click you make on your keyboard, every time you move your mouse, there's management system that looks at what that click or that communication message asks for, and then it changes things in response. And it's the same as in computer programming, but with the tradition of high performance computing being done in the background on the batch jobs because they're so big, the thought of interactive computing has been bubbling around and evolving for about the last 10 years. It turns out if you want to run a Jupyter notebook and do some high-end computing through your notebook, you need to be able to interact with the system live. And so that's what we mean by interactive high performance computing. It's real time. You get assigned to one of these precious compute nodes or cores running on that node, depending on your needs, and you're on it and nobody else is on it. You don't share it, and you can get some high-end work done. So, the reason we've got it is it does certain compute tasks like code development. You may need to compile, it might take you an hour to compile your code. You may want to run a real small version of it so you can real time see if it's working. You may be needing to explore data. It's used when applications have really large data sets that are perhaps remote, and you can move it on a high-speed network that you can't fit a petabyte of data on your laptop, unless you've got a really big laptop. And then user inputs that they come from the command line interface or an application GUI, graphical user interface, like Notebooks, MATLAB, and RStudio. And we support all of those on Expanse. And these actions performed on the remote compute node are the result of your input or program output. So, and for the people who've been around in HPC for a long time, it's really exciting to be able to offer this capability. And maybe someday we won't even notice that it's interactive or not. But right now you have to ask for that node so you can do things interactively. But we have ways to facilitate that. So motivations include you need more memory. Your job no longer fits on one CPU node, or it no longer fits on the system you've been on. So at the time I wrote this, it's 768 nodes with 128 cores per node and up to 256 gigabytes of RAM. So these are big, all right, and getting access to them is a privilege, especially interactively. Like my MacBook Pro, for example, is one node and 8 cores and 16 gigabytes of RAM. Now I could simulate MPI code on my laptop pretty readily, but it won't scale very high. So you need more memory, you need more compute power, you have too much data. And with machine learning and AI, that's really becoming prevalent. You have a lot of data and you need to move it in and out of your computation, or your network's just too slow. How many of you have a fiber optic connection right now? So we have large scale connections. I think we're faster than 150 gigabytes, but we're always getting connected to the fastest internet, which gives you some advantage for moving your data when your computing is done, or when you need to move data in to do your computing. My house, I get 300 megabits per second and 11 megabits upstream. It might have updated, they might have done that for me automatically. But when I wrote this slide, that's what I had that day. So a bioinformation lab, informatics lab I used to work with, would you use a FASTQ data set for every computation? 500 megabytes that came from Amazon S3, but they still had to get it into the lab. So, preloading the data can be a lot faster when you're moving between two high-end resources as opposed to onto your laptop. So that's why we have and why we support interactive computing. So graphically, or in this cartoon diagram, this is Expanse with all of its different nodes. And then you get some kind of session to connect you directly to one of these nodes. And Slurm will decide what that is. So you're sitting at your laptop and you submit a job to Slurm saying, I would like one interactive compute node, or so many cores on the interactive compute node. I need this much memory, et cetera. And Slurm will look and find which node is going to be available. And then you wait, and all of a sudden, you get that node and you'll know you're on because your login to node name changes. But that's basically what's happening. And it could take a while if the system's, really busy. So what kind of interactive HPC methods are supported and being developed? How you'll be interacting. You'll interact with your data when the job is done. You can do it on Unix. You can query file information. Like you get onto your interactive node, and now you can start looking at all that data that is over on the storage system, or even remotely. You can query the file, get basic Unix commands. You can look at the file contents. You can run visualizations like a NetCDF data browser. You can plot your results using some kind of application or a command line driven graphic utility like GNU plot. We don't necessarily recommend these, and I'll talk about that in this talk. And data visualization applications, NetCDF, HPF, TAO, ParaView, and the portal also allow you to run data visualization apps, and I'll talk about that. These data analysis platforms like MATLAB R and Jupyter Notebooks, we support those on the Expanse portal. And I'll say it several times, that's the best way to start running these. So this is just a visualization of Jupyter is really interactive HPC computing. You can run them on the remote, on the HPC node. You can run them on your local laptop as well, but they won't be HPC. The Jupyter architecture, this just shows the NERSC multi-computing environment. MATLAB runs in parallel now. And then ParaView is a very wonderful graphic application that we support on Expanse. We also have the user portal, which gives a web-based access to a lot of these applications. And it simplifies your access to them and manages a lot of the login. It gets the interactive node for you and launches Jupyter Notebook for you, for example. We have a webinar on that you can find if you want to learn more about it. But it's really the right place to launch MATLAB RStudio and even Jupyter Lab and Jupyter Notebooks. I highly recommend you guys start learning how to use you can also submit parallel jobs. Okay, so a big warning about interactive services. They provide access to the HPC file systems often over HTTPS at Expanse, but some interactive services don't give you a secure connection. For example, Jupyter out of the box is not HTTPS. And so we have a service called Galileo. I'll talk to you about that in a moment. But you want to make sure that when you do connect, this shows an insecure connection. Right now, that is what we consider to be an open password and open access. And if you were working in a Starbucks and walk away from your laptop, somebody could get in and hack your system because that's directly connected to your account on Expanse. So we want you to use secure connections. When you choose insecure ones, your account can get hacked. The portal is always secure. And then how to access these nodes, and I'll talk about how to keep them secure in the next few slides. So when would you need to use an interactive node? Again, the application is interactive, MATLAB notebooks. You need to stage large amounts of data. You want to run an AI application like PyTorch. You can run PyTorch and TensorFlow through a batch script. You can get work done in the back end, or interactively through secure connections. So you can run AI applications. We recommend that with a container, and we have a talk on containers. If you need to compile large complex applications, sometimes they do take a long time. An example of Java code that's 1 million lines took 30 minutes on a Dell 5511. So there's a lot of legacy applications that take a long time to compile. So how do we do that? The interactive compute nodes on Expanse, the way you do it is we run a command to activate that request. This gets SRun submits the request to the Slurm scheduler, and we're asking for a GPU or a CPU connection. And these examples, by the way, you can find them in the Expanse user guide. Always the most recent version. So if you've been using anything and it's no longer working, go back to the user guide because it gets updated frequently. You have to ask for like the number of tasks, the memory, number of GPUs, the time. And I noticed I have a CPU example here. I'll fix that when the talk is over. I'll get that updated. So here's an example of using an interactive CPU node, srun command. I want the debug partitions. The different partitions do different scheduling. So debug is 30-minute limit, but that's guaranteeing that jobs will not run for days or hours. I think we have a 2-day limit on expense, but you can get something pretty quickly. It's a good way to just do a quick debug of what your code you're working on. But in this case, srun on the debug is still limited to 30 minutes. So you have to pick a different partition. If you want to be longer on the interactive node, you need an account to associate that with. And then this gives the bash environment you want to launch. And what happens is you submit it and it gets sent to the Slurm scheduler, like I just talked about. A few minutes later, it could be 1 minute, it could be 10 or 15, it could take a long time. It all depends on how busy the system is. But here I've got a job ID that I can track to see where it is in the job queue. And then all of a sudden it's running. And how do I know I'm on a node? Is whereas before I was on the login 01 node, now I'm on the expanse-9-55 node, and I landed in my Calc Prime folder, which is where I called the interactive. Once you get onto that node, you'll see all your home files are mounted onto that node. So you can get access to all of your code. And we do have recommendations for where to run jobs from and where to put your data. And that's in one of our complex webinars on batch computing. So what I'm going to do is I want to try and just run a very simple code to calculate MPI prime. And this example is in one of our repositories. So I configure the module environment. By now, you hopefully have encountered modules on Expanse, and you've looked at that, a webinar on that includes that discussion, but you want to make sure you have access to the right software. And then I'm on the interactive node, I can run parallel code. I can't run this on the login node. That's not allowed. And so it runs and I get my result. Whoops. And so on the next slide is an example of getting a GPU node. How do I know I'm on a GPU node? NVIDIA-SMI returns GPU information. I could run that same code if it's compiled for GPU. Remember, the code has to be compiled to run on GPU or to run on CPU or to run on hybrid. And we support all three of those environments. Don't forget to exit the node when you're done. So you can use something called X11 forwarding to visualize and run an app outside of the portal. And the portal basically uses this, and that's how you connect through other applications, like to get onto an Expanse login node. There is some back-end communication between your laptop and the remote application, and it's pretty complicated, which why we no longer recommend doing this, but I include it just to give people some input in case they're on a different system. Complex webinars are supposed to work for general systems, not just one. And so X11 forwarding is a windowing system for bitmap displays, and it's common for Unix-like operating system. macOS uses Quartz to support X11, and it's architecture independent. So on my laptop right now, I have a keyboard, a mouse, and a screen. That's what I've got on my laptop. And I use the X server to exchange information. Like when I move my keyboard, information goes on my screen. And then there's clients, for example, the Xterm in the browser. But you can also do this remotely and connect to a remote machine and share data. And that's basically what X11 is designed to do. That's for X11 environments that are supported, like when you use SSH or on Mac OS. But what if you need to do it for your application? You can install X11 forwarding software like Mac OS Xports, use the connection command -SSH with a -Y, which means you want to exchange in your login environment some visual data, and try and get close. You have to install the software. This is just a simple example of getting Xports logged in. Xports installed. It's nothing magic, and on Windows you would do the same thing. But what we have discovered is that Mac OS, all versions now, don't support X11 properly, not anymore. A few versions ago it used to work. It still doesn't work, and I'll show you how painful that can be. It's the motivation for using the portal. but at least you'll have some understanding for like X11 forwarding to Expanse. I use Xports windows. I create two Expanse login connections, window 1 and window 2. I tell both of them that I want to exchange visual data, and then I get my interactive node on one node, and I'm logged onto it. And then from my other node, I can log on the other login. I can log into that node, and now both of them are there. And the reason I do two of them is this allows me to then try and run the MATLAB and monitor it from this other window. So GNU plot is another example of a code. GNU plot's been around for a long time. People embedded in their old codes, and you can use it to quickly visualize data on a remote machine if there's not a lot of it. I used to be able to do it in color, but the last time I ran it, it was black and white only. But I load the modules for GNU plot, and I also want to point out, look at the path to GNU plot. If you ever get frustrated with modules, just remember, if we didn't have module load GNU plot, you'd have to type out that whole location for GNU plot. And then if they updated the system and the versions changed, you'd have to update all that. Instead, you let the module system deal with it. So there's a lot of reasons for learning modules that, first of all, you have to, but there's a big benefit. Anyway, I've now got GNU plot loaded. I go into GNU plot and I tell it what kind of terminal I'm using, and then I can plot something. And inside your code, it might work well, but on the command line, you can do some visualization of data. But it's really hard now, unfortunately. It's just the way it is. And we don't see a solution for X11 forwarding. But other interactive examples, I've got a few examples that I want to start with. And here's another example of running an interactive application from the command line that I'm in control of. It's called NetCDF, and there's other more updated versions, but we do support NetCDF. There's a lot of data in the climate weather modeling ecosystem. That's NetCDF. I think there's HP CDF, and there's other versions that are also supported. But it's a binary file, so you can't just cat it out. It's compressed binary data, but it has information associated with your data. And I'll show you a couple of examples. And it has visualization tools and viewing tools. So you can install it. I won't take a lot of time for that, so we can get through to other examples and questions. But SciNet, this example is for a simple example provided by SciNet. We all know SciNet in Canada, and you want to get the right module environment, set up your modules, put the environmental variables into your bash script, build the compile command, and the example would generate a data.nc file, and then browse and query file contents. I include this not because I expect you to do it in your work, but some of you might, or you might find you want to play with it to understand it. So I'm showing my .bash profile. I'm on login to NetCDF. Here's the library commands that need to be in there and updating paths to the binary. And so now I'm in the NetCDF, and I load the right modules, and I look for NC view. So can I visualize and view my data? Yes, I can. And so I've got some sample C code that can be compiled, and then I've got some data.nc. So that's what's in the working directory. So ncd dump is a way to view the data, and it has a large number of arguments. Everything from looking at the variables to actually looking at the data, looking at timestamp data, what's in my file. And so I'm going to ncd dump this data simple.nc, and I didn't ask for anything in particular. And so here's what I get is just a basic overview of the variables. It's kind of nice. I can see the names of my variables and some of the values for some key variables used in the computation. And so I can also look at XML formatted output. And then you can ask it to show you some -t gives me some of the data. And the snip means it was too many lines to print. So that's just something I use in my talks. But it printed out the density and described the density, described the velocity, and started printing out the data. Of course, there's not room to show all of it here. So it's a way to quickly view more complicated data. And you might want to look at other alternates. You can also run something called NC View, which gives you the visual analysis of your data. So it's a real quick way. And this is best done, and you want to do this on an interactive node. Okay, so that's sort of an overview of a couple of data viewing applications beyond MATLAB, and well, MATLAB and R are part of that. But this one, they're a little more complicated, so I'll talk about them really quickly. I was able to do it by just going on and getting the right modules. So if you want to use something like MATLAB from the command line, you have to ask for an interactive node. We're waiting. We get the interactive node. We know we're on it. Then I load the modules for MATLAB. And I had to connect with a -y, right, in the connection. And then here are my modules. And then I try to run MATLAB and I try to plot. It doesn't work. MATLAB works, but the visualization didn't work, even though I asked to do a -y. So if you really want to do it, if you're really determined to run MATLAB on your own and not use the portal, you can, but it's pretty complicated. You need to create two windows, log on twice, so you have window 1 and window 2. And in window 1, you request that interactive node that gets you that interactive node. In window 2, you also connect to that interactive node. And now we're on this node, and then I load the modules and I launch MATLAB. Use the Expanse portal. All that works. Up comes MATLAB, but it is so slow, as you would expect. Running a visual like MATLAB or R, through the connections that have to go from the interactive node back to you on your laptop, it's very, very slow. So you can't, I put this in here to show you, you can, but why would you want to? It's so complicated. The portal, they've done a lot of work fixing the back end so it's a strong, consistent, secure connection, and MATLAB runs for you. It's using the open on demand portal, open on demand software infrastructure that allows us to submit jobs and run jobs on it. Systems like Expanse. On TSCC, they do support running MATLAB from the command line, but again, it's still slow. So Jupyter Notebooks, you also want to be able to run Jupyter Notebooks, and they can be done through the Expanse portal. You can launch them, or you can also launch them with a tool called Galileo. I'll talk about that in a moment. Just check my time. Now we're getting through this well. So what's Jupyter? Most of us know, and if you don't know, go learn about it. It's, to me, the first time I got into a Jupyter notebook, I went, oh my gosh, I'm inside my code. I just found that phenomenally exciting, and to be able to change the value of a variable without having to recompile. That said, your code needs to run in Python, best using Python, but there are Fortran environments and they work. But just to be inside your code is why Jupyter is so popular, and it's really popular for analyzing data and visualizing your data. And so you can install it locally on how can you run it, and then how can you connect to HPC systems. If you've used notebooks, you know that you install something called Anaconda. It's the best tool, and that'll be local. And you can install Anaconda environments on the remote machine. But we don't recommend that for either. The default is HTTP. These connections are not secure. And that means, like I said, that connection through that web browser, first of all, is you can have it be sniffed through SSH on something monitoring your messages between your laptop and the remote system. So we want it to be HTTPS, so at least your messaging is secure. So you can run it remotely, launch Anaconda, and then you can connect over HTTP and launch a Jupyter notebook through the command line interface. You can make it secure by using SSH tunneling. That's secure, but very inconvenient. The tunneling, you have to know and grab an a port that's available on the machine, on the node that you want to run it on, and it has to stay up. And the ports are notorious for going up and down. You can connect over HTTPS using the SDSC satellite reverse proxy service and the Galileo client. Galileo you can run on you log in, you run Galileo, and it takes care of everything. And so you don't have to worry about the scheduling. You just tell it, you don't have to write a script. You just say, get me a connection that launches notebooks, sorry. And then you'll be able to navigate. It'll launch you onto the remote host like Expanse, and then you can move to your notebook directories, or you can tell it exactly where your notebooks are. It's great. So you can do quite a bit with this connection. But remember to treat that notebook URL like a password. Okay, so SRPS, just to give you an idea, inside the internal network of a cluster where you have multiple racks, multiple nodes, and a lot of cores on those nodes, the interconnection network is what we call that. It's very complicated. And you don't want to have to worry about navigating through that. But what the reverse proxy service does is you ask for a connection, you'll get back the location for a Jupyter notebook. And in the meantime, this SRPS is going around and finding your node and building a secure connection between your laptop and that Jupyter notebook connection and the whole system, so that it's all done over HTTPS. But the idea is that the notebooks are hosted on the internal cluster network as an HTTP service, but then there's an HTTP connection at the edge of the cluster that is HTTPS. So let's go, yeah. So SRPS can run on any HPC system, and Galileo is the command line shell utility that Marty Candace has been leading the development of, and it helps you submit your job. It orchestrates your interaction with the Slurp scheduler, getting that remote node, launching whatever environment you need on that. You don't have to do module load. It'll load all that for you. Now, if you decide to do something different, you might have to modify that module, but you tell Galileo what you want, and you'll get an HTTPS connection. And it supports containers, and you don't have to install a conda environment. You can if you want to, but we recommend you do your work through Galileo. It generates that batch script for you. It records a copy of it so you can go back and look at what Galileo was doing for you. And it's command line argument driven. You just go in, run, send, I'll show you an example. But this is the system logically a virtual layout of here's all the nodes, the racks and nodes, and interconnection network is here. And internally, it doesn't need to be HTTPS because the only access to the internal is through the login nodes. So we're controlling that connection, and you have to SSH in. There's no other way to connect. And so what happens while you've submitted the request, the SRPS works with the system, a node gets identified, a connection, the browser, the Jupyter notebook gets launched, and then this HTTPS connection gets connected to the internal connections that SRPS is managing for you. And so what happens is you're going to fill out the Galileo command with different values. You have to tell it the account. And there's on that link, I point out at the bottom of this page is a link to interactive training connection. And also there's a link to the Galileo system that I think is in later slides. If not, somebody can put that in the chat for you guys. But you submit this request. This launches the satellite reverse proxy service. You have these status icons that let you know when things are ready. When they're all 4 green, your URL that you got launches, and it's populated. You get back the URL, the notebook URL, as a response from Galileo. And then you paste that into the browser and you wait for it to get activated. So this is more details on Galileo. make sure we have plenty of time for Q&A. And the steps that Galileo goes through. Here's a real example. I make sure I've got Galileo in my path. If not, you have to export, put this into the path. You could put it in your bash script or just do it for that one login that you're doing right now. You find that you've got Galileo. Here's the command to launch Galileo. Or for shared partition, you need your own account. This is not a real account. You ask for 2 CPUs, 4 gigs of memory, 30 minutes, and some environment modules that you want to use. And then you get back a message that the request has been submitted to Slurm. You know what Slurm is now, and here's your Slurm job ID. And then you get back this web link and copy and paste that and keep it, because it goes away unless you've saved it. But that's where your notebooks will, your connection to Expanse will show up. And you can even tell Galileo what directory you want it to start up in if you have a directory containing your notebooks. Otherwise, you can just navigate through the notebooks. All right, so here we're waiting and waiting until it's running, and then eventually you get your notebook populated. So we tried to simplify the getting a notebook and getting things to run. This is an example of me checking for one of the notebooks that got launched. And they're running, so that means my jobs are running. I have an allocated node interactively. The notebooks run interactively. Here's an example for GPU. It's identical, with the exception of the GPU the GPU and the partition that you want. So here's an example of what you'll see. These URLs are pretty wonky on purpose. So we have a list of wonky words and put them together to make a secure, hard to hack and create on your own URL. And I launched it, so I start right in my notebook directory. You can navigate just like you can with Jupyter Lab, and you have all the Jupyter Lab features you could want. And here I'm on a GPU, and I'm running some commands in the notebook to see, am I on a GPU? So we have a collection of Expanse notebooks that are tested and updated periodically. It ranges from Hello World on CPU and GPU to a little bit of machine learning or some other materials from our different training programs and institutes. The idea is to give you something to start, like having a Hello World notebook is good to have available when your notebook stops working. I always recommend people have that for whatever they're doing. All right, gateways and portals. I don't know if I can say enough about the Expanse user portal. We find it so useful now that we create training accounts behind the portal for all of our training sessions, because it guarantees people can get on and get things working. It supports MATLAB fully and R and Jupyter notebooks. And you can do job creation. You can navigate and manage files. You can even edit if you want to do it in that mode. So it's very powerful and simplifies your access. So if you're not needing to be on the command line compiling and debugging, take some time to learn the portal. There is a user guide link up here, and we do have a couple of webinars in our on-demand catalog. And that's the link to the portal. You would use your Access CI login credentials to get in there. And it is dedicated to Expanse. And I think we're putting up another OOD environment in front of TSCC, but I couldn't guarantee where that is. Portal has file management. You can also navigate or launch a Jupyter Lab shell and running MATLAB. Every time you request to launch MATLAB or the notebook, you are going to it'll show your status in the queuing system through the portal. So all of these go through Slurm, just like we've been talking about getting jobs queued up. They queue up, and then once you get them, they're running for as long as your time allotted. Launching a notebook, there is an input form here that can be used for launching notebooks. And same thing, you'll get a session, it gives you the URL, and you just wait for it to get launched, and you have access to your notebook. For informational purposes, this slide, if you know your account, don't use 300. That's not usable for everybody. But this is an example of how to fill in those form elements for general purpose testing, just to get you going. I do want to point out that we use Singularity, and so you need to find the Singularity container. And here is the location for all the Singularity containers we maintain. PyTorch is a general one that you can use for all kinds of notebooks, not just machine learning. And the same with TensorFlow. But if you go in there, there's PyTorch, TensorFlow, and other kinds of containers. And if you need something, reach out to consult at sdsc.edu. They can make sure if there's a particular version that you need to work with, they'll help you with that. And so you want Singularity Pro as the minimum environment variables. So don't change anything. Try all, just try these and it should work for you. And that's the end of my talk. Thank you for your attention.